Okay. Today we're going to talk about estimating a multinomial, a sparse multinomial. So, of course, what's sparse is not the multinomial but the estimation. So I should say sparsely estimating a multinomial. What I have in mind is a specific kind of multinomial, P1 through PV, where V is a very large number. It's not 4 or 5, but it's 100,000. And say from counts, we'll call the counts sometimes C1 through CV and sometimes X1 through, say, C1 through CV. And the common situation is that the counts are, many of them are 0, and of the remaining many are 1, and of the remaining many are 2, so it's a very long tail of counts. That's the situation we've dealt with when we talked about good Turing. So the first method is simply a maximum likelihood estimation. And in maximum likelihood estimation, P hat maximum likelihood of I, of word I or event I, is simply count I over n. Right? And we know the properties of the maximum likelihood estimator. The estimator that gives you all the I's, the entire array, is unbiased and asymptotically consistent and maximally efficient. It has this little problem that it has high variance for low counts. But unfortunately, almost everything is low counts. Not everything, but most of these I's are low counts. So maximum likelihood would not be a good estimator. So the second estimator we discussed was the good Turing estimator. P good Turing. Word I, P of word I and PI are kind of the same thing. I'll just be consistent. PI good Turing. Now that was dependent on the actual count that we got. So P of word I, given that the count I is R, P good Turing, was, I think, was it R minus 1 times n of R minus 1? No, R plus 1 times n of R plus 1 over n. Was that right? No, divide by n of R times n, right? This was our correcting factor. Now, do you remember that I was kind of looking at it and saying, am I forgetting something? And I told you if I discovered that I forgot something, I'll correct it that afternoon. Well, I didn't forget anything. That's why I didn't correct it. It was correct. But I'll tell you now what was bothering me. What I'm used to doing is comparing this estimate to this estimate. And compare it to the maximum likelihood. The maximum likelihood in this case would be R over n. So the discount factor, or the good Turing discount factor, the amount by which we will typically discount from the maximum likelihood estimate, would be this divided by this. Okay? So let's say R equals 1. This would be 2 times n sub 2 divided by n times n sub 1. And this would be just 1 over n. If n is 1,000,000 words in the corpus, the maximum likelihood estimate would be 1 over n. So if I divide this by this, I get a more symmetric looking formula, r plus 1 times n r plus 1 divided by r over n sub r. This is the formula I remembered, and it didn't look right to see this. But it's because I remembered the formula for the discount factor as opposed to the formula for the original estimate. So for, let's say, for singletons or for novelty, the discount factor would be 1 times n1 over 0 times n0. So that doesn't work because we don't know the size of the vocabulary. So you can say it's not a discount factor, it's an up factor, it's an infinite up factor because you're going from 0 up, so that doesn't make sense. Say infinite. Going up by an infinite amount. So we're going from 0 to something else. But more meaningful, for singletons, the discount factor would be 2 times n sub 2 over n sub 1. For doubletons, it would be 3 times n sub 3 divided by 2 times n sub 2. And I mentioned last time that in practice, for most corpora, large enough corpora, this could be maybe 20%. So I don't know if I call it the discount factor or the correction factor. The discount would be 80%. The correction would be by a factor of 5, down to 20%. So instead of 1 over a million, it would be 0.2 over a million. And this would be somewhat less, maybe a factor of 2 correction. And for case of 3 and 4 and 5, it'll be closer to 100%. And then when you get to 6, 7, or 8, it will be very close to no change. At which point we can stop. All right, so we talked about this at length. Now I'd like to talk about other estimators. So here's a third estimator. Floor. Put a floor. What does that mean? It means that PI would be something like the maximum between Ci over n and some floor value. The floor value would typically be less than the estimate of for the singletons. So maybe a singleton would be 1 over 10 million, and the floor value would be somewhat less than that. Or it could be even larger than that. And I didn't write it equal here because it would just be proportional, right? Because I will need to re-normalize this. Whatever floor value I use, I will need to quickly sum over all the vocabulary, see what it comes to, and then multiply it by a constant here to make it all sum to 1. So I don't have much to recommend to this, except it's very simple. You can choose a floor value by some kind of held out data. We'll talk about that in detail. But I don't know much about the properties of this estimator. It's clearly a nonlinear estimator, whatever that means. It has this max operation. Max operation is never linear. So I don't know. I wouldn't go for it, but I just mentioned it here. But let's see something a little more interesting. Yes?
I have a question about 2.
Sure. Sorry, I forgot to ask if there are questions here.
So what is n sub r or n sub some number?
N sub r is the number of words that occurred exactly r times in the corpus. So n sub 1 is the number of words that occurred once, namely the number of singletons. Number of word types that occurred exactly r times. Yes?
So is n equal to v? R over n?
N equal to v. So I gave 2 equations last time. One was, all of the n's, yes. nr r goes from 0 to infinity equals v if the vocabulary was defined in advance, then there is an r sub 0, words that did not occur before. If the vocabulary is defined only as the words that occurred, then there is no n sub 0. Then you start from 1. But yes, this is true. And the second thing was, if you sum n sub r and multiply it by r, and now it doesn't matter if you start from 0, this should be n. I gave these two equations last time, right? Question? Okay, let's look at slightly more interesting estimator. There's a way to smooth. PI, I can call this PI floor. Call it Li for linear interpolation of I is P maximum likelihood of I plus 1 over V. This with a lambda and this with a 1 minus lambda. So it is a linear weighing of two different estimators. This is the standard maximum likelihood estimator, the one that's just Ci over n. This you can think of as the uniform estimator. It assigns 1 over V to every word. It is an estimator. It's strange it may be strange to think of a constant as an estimator, because we're used to thinking of estimators as functions. But a constant is a function that doesn't do anything, but it's a function. What are the properties of the constant estimator? What is the variance of a constant estimator? 0. It does not depend on the data. Okay? It always gives you the same answer regardless of the data, so the variance is 0. What is the bias of the constant estimator? 0? I wish. Then I would have an estimator with 0 bias, 0 variance. I could go home.
I mean, it would just be like large?
It could be large. It would be whatever the true value is minus that constant. Right? Bias, we said that bias of an estimator is the expected value of the estimator minus the true value. This is red. Well, the expected value is just 1 over V. It's constant. It's always, the expected value is the same as the value that you always give. So it is whatever it is. But the important thing is the variance is 0. And we expect that the bias would be larger than the bias of a smarter estimator, because it's a very dumb estimator, right? What is the equivalent of a constant estimator for a coin? Well, that would be one constant estimator. So that says probability of head is 1, probability of tail is 0. What about saying that it's fair? That's another constant estimator without looking at the data. Or even if you give it data, it ignores the data and says it's 50-50. But even if it always said it's 70%, 30%, that would be a constant estimator with a different constant. Right? The property of a constant estimator that does not look at the data. It doesn't change its mind based on the data. But it is an estimator. A uniform constant estimator is the one that says the coin is fair, 50-50. So I'm going to use a uniform constant estimator. I'm sorry, it's not the whole thing, it's just this part. I'll even put a hat here. It's kind of a joke because it's constant, but just to remind you that it plays the role of an estimator. Uniform constant estimator. So this is an estimator, a bona fide estimator, and this is an estimator. And I'm combining them with linear combination with the weights. Question?
Can the weights lambda depend on the i's, or do they normally be
It could, but then you would need to make sure it normalizes properly. Because remember that the rule is that when you sum this over all, but yeah, otherwise, sure. Let's start with the case where it does not depend. I want to give you sort of an intuition of what's happening here. First of all, you should recognize that probability distributions are convex sets. Remember, we talked about the probability complex being a convex set, which means that any two probability distributions, any way of weighing them together produces another probability distribution, right? So you can think about this estimator as sitting here in a single point. And you can think of the maximum likelihood as sitting here, single point. This is a point in n-dimensional space, in v-dimensional space. And now you can pass a line through them. And any point on this line corresponds to a particular weighted combination of these two. So here, let's say we put the lambda here. So when lambda is 0, we're all the way here. When lambda is 1, we're all the way here. When lambda is a half, we're here. And when lambda is 0.25, let's say, we're here. So we can move along, we're moving along this line. What does moving along this line means? Suppose you use this method, suppose you use the maximum likelihood estimator only, and you're using it based on data that you collected today. Because the estimator has variance, it would fall somewhere here. And if you use a different data set tomorrow, it will fall somewhere else in the space. And if you use another set of data the day after, it'll fall somewhere else, right? That's what we mean by the variance of the estimator. It depends on the data. So I can imagine that this point might be the mean of the estimator, which, because we know it's an unbiased estimator, is also the truth, right? So the truth, the real distribution is here. So this is the truth. Call it P sub t. And the maximum likelihood estimator itself will be dancing around it with a radius that corresponds to the variance of this estimator, or to the square root of the variance, to the standard deviation of this estimator. Right? This is the truth. This is the expected value of this estimator before we saw data, or after integrating over all possible data samples in the world. Because it's an unbiased estimator, the center of this cloud is on the right point. But any particular estimate that comes out of a particular sample will land somewhere in the area, right? So we can imagine the estimator as a cloud, maybe a Gaussian cloud, maybe not so Gaussian, but it's a cloud nonetheless, whose center of gravity is on the truth, but it spreads out quite a bit because it has a wide variance. Now let's look at this estimator. This estimator doesn't have any variance. So no matter what sample you give it, today, tomorrow, or the day after, it will always give you back this point. So this cloud happens to be a single point. But this point is quite far from the truth. Okay? Now what does the linear interpolation do? Instead of being here, we are maybe here. So instead of standing far away and throwing a dart at this point, we're standing closer, so we have a lower variance, but throwing a dart at a point that's a little bit off. So the target we're aiming the dart at is the bias. Here we're aiming the dart from far away. Right at this point, there's no bias. But because we're standing far away, we may end up, further apart. Here is when you stand really close to the board and you just nail the dart right in. No variance. You always get it right, but you're aiming at the wrong place. And this is somewhere in between. So what this represents is the bias variance trade-off. As lambda gets larger, remember lambda grows in this direction, right? 0 here, it's 1 here. As lambda gets larger, what gets larger and what gets smaller? As lambda gets larger, I'm sorry? Variance gets larger and bias gets smaller. That's because I chose to put lambda here and not here. If I swap these, it would be the other way around. But basically, as we use more and more of the maximum likelihood estimator, which has 0 bias and large variance, we're moving more towards a high variance and low bias. And as we use more this constant estimator, we're moving in the opposite direction. This does not have to be a constant, by the way. This could be a smaller variance. In principle, you can combine two estimators that each have their own bias and variance, and by linearly interpolating them, you can move along the trade-off. The bias of the combined estimator is very easy to calculate because bias is a linear operator. So the bias is just a weighted sum of the biases of the components. The variance is a little bit harder to calculate. Sometimes you can, sometimes you can't. Depends on the specific likelihood function. But you do know that the variance is going to be in between these two. What's the optimal way of combining them? That depends on what your goal is. If your goal is something like mean squared error, remember that mean squared error is the sum of the bias squared plus variance. So you can definitely find a particular lambda that minimizes that. If your goal is something else, which is like likelihood of new data, which we will focus on mostly, then you can also try, maybe using some held out data, you can try which lambda value would give you the optimal point. The important thing is that you have a choice. You have a whole range, continuous range of choices you can choose among very easily by choosing the value of lambda. This is not restricted to combining two estimators. You can think of having a third estimator that is maybe intermediate between them. It has smaller bias, so it's closer to the truth, and somewhat smallish variance, not as big as this one, but not as small as this one. And now you can think of, you can connect these three estimators. So what I'm connecting here is the centers of the three clouds. It just so happened that this is the truth also. But I'm connecting the centers of the three clouds. And now anything inside this triangle is in this convex hull represents a whole set of interpolated solutions of the form lambda 1 times the first estimator plus lambda 2 times the second estimator plus lambda 3 times the third estimator, such that sum of the lambdas is 1. So any linear interpolation of the three corresponds to a particular point here, and vice versa. And I guess you can ask yourself, what is your objective? What is your optimality criterion? And try to find the set of weights that optimize that criterion. When you use interpolation to trade off bias against variance, the term statisticians use is shrinkage. The reason they use the term shrinkage, because they typically think of this is the large variance estimator, and this is the small variance estimator, and you're shrinking the large variance estimator towards the lower variance. You're shrinking that cloud. Typically, the large variance estimator would be the better estimator in the sense that it's centered on the right target or close to the right target. But you're going to shrink it to get rid of variance. The simplest way to get rid of variance is to interpolate with a constant. The constant is then represented by a cloud that is a single point, because the variance is 0. But you could also shrink towards a different, just smaller variance estimator. Questions?
Really interested. What is the advantage of this kind of smoothing, shrinkage over the good Turing correction?
Good question. Well, I can think of a disadvantage. I described here a rule that applies uniformly to all the words in your vocabulary. Another way to write it is to think about it as interpolation of vectors rather than interpolation of one word at a time. So the PML would be a vector. So it's a vector of size v. And the constant would be a vector. So it's a vector of where every element is the same value, 1 over v. And you combine them, lambda times 1 plus 1 minus lambda times the other. So think about it as either same rule applied to all the i's, or is just the same rule applied once to the entire array. You're interpolating 2 arrays. Now back to your question. For words for which the count is large, let's say more than 50, the maximum likelihood estimator is very good on its own. Its variance for these particular words is quite small. So you are now combining it with another estimator, which also has very low variance but has a significant bias. So you're taking the word the, which the maximum likelihood estimator told you occurred 50,000 times out of 1,000,000 times. So you know it's 5%, and you know it's quite accurate. And you're forcing it to be weighted with a very stupid estimate, which is 1 over the vocabulary size, which is, of course, very wrong for the, right? So you're using the same smoothing rule for all the words. This smoothing rule is very bad for common words. It might be better for very rare words that occurred 0 or 1 times. But you're using the same rule for everything. So I would say good Turing would be better. I still need to introduce this because this is the most general kind of way of introducing shrinkage, and we will use it in cases where you don't have that much data, or but it is the case that just with the setup that we discussed, good Turing will do better, will do significantly better than this. Another way of thinking about it, I'll get to it in a second, is we have to choose a lambda, but we have to choose the same lambda for all the words. And it doesn't make sense. You want a lambda that, for words that were seen many times, weights us heavily towards the maximum likelihood solution and barely uses this. And words that were seen fewer times maybe uses this more than that. Malcolm?
That's what I was going to say.
Okay.
Couldn't you just have a lambda per term you're trying to estimate?
You could. You could. You may be better off putting them into categories. When we talked about how you estimate the lambdas, we can revisit it again. Okay. There are actually 2 ways of understanding shrinkage, one corresponding to the frequentist way of thinking, one corresponding to Bayesian way of thinking. So the term shrinkage is a classical frequentist term. I'm sorry, the term bias and variance is a classical frequentist term. And therefore, shrinkage is also thought of as a frequentist approach. Estimators have bias and variance. Regardless, you don't need to assume any prior on things to define what a bias and variance are. Remember, the frequentists think of the world as being fixed but unknown. And whatever the value of the world is, whatever the true distribution is, you can define a bias and variance relative to that. So from the frequentist point of view, this is sort of the explanation. You have these clouds that represent variances, and you're trading off between them to create smaller crowds that are still somewhat close to the truth. From a Bayesian point of view, you can still explain why linear interpolation might work, and that is, in a Bayesian world, not quite. No, I'm not sure I can do it with this, so I need to introduce one more thing. So I want to tell you about a case of shrinkage that is taken to an absurd extreme, and it's called Stein's paradox. And I encourage you to read up on it on Wikipedia or wherever. Stein's paradox says that suppose you want to estimate the average basketball betting score for this coming season of baseball betting score for the coming baseball season. So you collect some data from previous year's baseball, and that would be pretty good data to base your estimate on. But you also collect two more data sets. One is of alpha radiation in the nearest star, and the second one is the amount of corn eaten in Uganda 20 years ago. Stay with me. And Stein's paradox tells you that if you build a simple estimator for each one of these three estimators, one of them estimates the baseball, one of them estimates corn consumption, one estimates alpha particle emission, shrinking them together will give you a better estimate of baseball next year than using just the baseball. Yeah, your reaction was just right. What it tells you basically is that you can shrink, you can benefit from shrinking even when the other estimators have nothing to do with the thing you're trying to estimate. What does corn consumption and alpha radiation have anything to do with baseball? And yet, mathematically, you can prove that the estimator would be better in the mean squared error sense than if you only used the data that's relevant. It basically says use any data you can, whether it's relevant or not, which is a crazy notion, right? Completely crazy. Before you run home to write your baseball betting program, I should tell you that it's a very highly theoretical result in the sense that it doesn't tell you how much better it's going to be. And it doesn't even tell you what the shrinking coefficients should be. It just tells you that there is a set of shrinking coefficients that will do better than just using one of the data sets. Let me try to argue for it numerically. Your baseball data gives you an estimator that is centered on the truth, right? It's unbiased, and it has a certain variance. This is the truth about baseball. Now your alpha radiation estimator gives you an estimator that, of course, has nothing to do with baseball. It's somewhere in the space, and it has its own variance. It might be large, it might be small. Let's say you have a lot of data here, so the variance is quite small. And then you have the corn consumption. And that would be another thing. Now, if you connect these three, you have the triangle inside which all of your interpolated estimates are. And what Stein proved was that the optimal point, from the point of view of mean squared error, the optimal interpolation lies strictly inside the triangle, not on the boundary of the triangle. Now my guess is it doesn't lie here. It lies here, like an infinitesimally small distance from the edge. And the amount by which it improves on the actual edge is infinitesimally small, like negligibly small. But mathematically speaking, it is better. Stein's paradox only holds for 3 or more sources, not for 2. Don't know why. Now I can tell you how Bayesians explain it.
But in this case, if we took the data closer to the football domain, say football data or something like that, so wouldn't you be essentially reducing the bias along the triangle, and your magnitude of deviance from the true value of baseball would shift more if you had the data from, say, related sources rather than from radiation?
Right, right. If you had data, if this was not corn consumption, if this was baseball from 20 years ago, then yeah, it would be here. And then the optimal point may well be a noticeable, appreciable distance away. And you would have a real improvement. I deliberately took a case where you don't expect any improvement. And the theory tells you that there will be some. The frequentist way of looking at it is to say, I don't even know how to explain it except to say that it's this entire triangle and the optimal point is not on the edge. Kenton?
Yeah, does it matter if you have like larger variances for the other things? Let's say your alpha radiation, your corn were huge variances.
I don't think so. I don't think it matters to the Stein paradox proof. It has to have some variance.
Okay.
The Bayesian interpretation of this is that there is a true parameter set that represents baseball. And there's a true parameter set that represents corn. And there's a true parameter set that represents the true distribution of alpha. But they all came from some meta prior. So there was a prior distribution over all parameters in the world. I guess it represents God's distribution. And God chose what the parameter is for corn and what the parameter is for the alpha distribution, what the parameter is for baseball. And now from these distributions we got data. This is data, different types of data. And the reason that we can have a better estimate of this by also using these data sources is because there is a connection. We are basically using these data sources to learn something about the prior and then come back and help us. Of course, these are so far away. This prior is so crazy wide, non-informative, that you don't learn much. But there will be cases where you can actually learn from this data about this, and this is exactly the case you talked about. So let's say these are not as crazy as we thought. This is baseball in the 1990s, and this is baseball in the 1980s, and this is baseball in the 2000s, and so forth. Now you can imagine that, yeah, there may be a relationship here, and I should be able to learn from this data. And one way to do it is through a hierarchical Bayes model like that, that says that, you know, baseball overall is getting better with time, or overall it's getting around some kind of a mean and with some variance, and different decades fluctuates randomly, or some kind of a story. Kenton?
When we draw a simplex like this, or this triangle, are we like 100% saying that we are having some sort of relationship between them that can be represented in a model like that prior?
When we draw a triangle, are we saying that each point,
Three different, yes, stuff like that.
right, is there like a direct relationship between this and this?
Yes.
I don't think so, because here it's not just a question of weights, it's also a question of what the prior is.
Okay.
Shrinkage, other than Stein's paradox, shrinkage is a very commonly used method in estimation. Sometimes you shrink with the constant estimator, sometimes you just shrink with the lower variance estimator. The advantage is they're very simple, simple to implement, simple to combine, and we're going to discuss soon how you choose the lambdas. Not only for combining 2 models, which requires only 1 lambda, but for combining 10 models, which requires 9 lambdas. The disadvantage is something you've picked up on already. It uses the same rule for combining the estimates, the same weights, the same lambdas, for combining the estimates for every word or for every event. And one might argue that some events might be so well estimated by the lowest bias model that you don't need to combine it with things. Another slight weakness is that you select the weights maybe once, and then they don't depend on the amount of data you have anymore. And if you get more and more data, you might argue that you want to re-estimate the weights. So they do not automatically, the weights do not automatically scale with the amount of data that you get. Why would you want to change the weights when you have more data? What changes when you have more data, the bias or the variance? Variance changes when you have more data. Does bias change? No, the bias is bias. Well, typically it doesn't. Sometimes bias, if there is real bias, it's sometimes a function of the data. It also goes down. But generally speaking, variance almost always goes down as you have more data. So if you have 2 estimators, one of them with high bias, the other one with high variance, if you have more and more data, go for the one with the high variance because it has lower bias. If you have less data, go for the one with lower variance. So how you combine the 2 will depend on how much data you have. And this formula doesn't tell us how to, it doesn't do it automatically for you. I want to show you a different method which does do it automatically for you. And this method is called pseudo-counts. Where? Did I cause damage here? Am I still on? Aaron?
Good.
Thank you. So the method I'm going to show you, I'm pretty sure you're mostly familiar with. You take your categories of words, word 1, word 2, word 3, all the way through word V, and you represent them by buckets. And you're going to put the counts from the training data into the buckets. But you're worried about the buckets that are going to remain empty, right? Those that you have never seen. So you're going to be somewhat socialist. And you're going to give everybody a little bit to start with. Let's say you give them 1 count to each. And then you pour the data, the real data in. So this one will have C1 plus 1. This one would have C2 plus 1. This one would have C3 plus 1, and so forth. So the general formula would be PI. The estimate for PI would be CI plus the pseudo count, call it K, in this case it's 1. Now you have to normalize it. Normalizing it is easy. You just have to remember how many pseudo counts you added. So this will come to N plus the number of pseudo counts per bucket times V. So you're somewhere, compare this to interpolation with a uniform. By putting the same count of 1, or let's call it K now, putting K into each bucket, before you threw data in, this is like a uniform estimate, right? But now you pour the data in, it's no longer uniform. But it's not maximum likelihood either, it's somewhere in between. So it's a different way of moving between the uniform and the maximum likelihood. But it's not identical. One big difference is that this automatically adjusts to the amount of data you have. Namely, if you have a ton of data and you accumulate more and more and more data so that every word was eventually seen many times, so you don't really need to smooth, this will go in that direction because the initial k pseudocounts will not matter much. Right? So when n goes to infinity, this goes to the maximum likelihood estimate. The fixed k will become negligible relative to the counts, as long as the counts, all of them, grow to infinity. But they will. If this goes to infinity, they go to infinity too. When n goes to 0, this goes to the uniform. Right? That's not even in the limit. It's when n equals 0. But the closer n is to 0, the closer this is to the uniform, because everybody is k over the same constant. So we achieved something that we didn't have here. Here we would have to re-estimate the weights. So compare the example of n equals infinity. N is very large. This automatically gives you the maximum likelihood estimate. But if you stick with the weights you estimated a long time ago, then with lots and lots of data, the maximum likelihood estimator here would get better and better and better, but it always gets interpolated with a uniform distribution, which is going to make it worse. So the correct thing would be to re-estimate the lambdas. There you don't need to re-estimate anything. It doesn't matter how much data you put in. You got an automatic weighing of the uniform versus the maximum likelihood. Now, what k should we use? People often use 1. That's known as Laplace method, I think. It's been used hundreds of years ago. But why 1? Why not 2? What's the difference between 1 and 2 or any other number?
Affects how much smoothing you're going to get.
Okay.
If you use a really large number, then you need even a higher amount of data to overcome.
Right. Right. So in both cases, whether you use 1 or 2 or 10 or any number, in all these cases, you're starting with a uniform distribution. But as you start throwing real data counts in, it would matter whether you started with 1 or 10. If you started with 1, your data would have an easier time overcoming the uniform assumption and pushing it towards the empirical distribution. If you use 10, you would need 10 times as much data to do that. So using a larger pseudocounts corresponds to having a stronger conviction that it should be more uniform. In the limit, if k is very large, let's say 1,000, if you tell me to estimate with 1,000 pseudocounts in every bucket, you're basically saying, I am pretty sure that all words should be equally likely, and you would need a ton of data to make a difference to that, because if you only threw in a couple counts to each word, it will not change much. We're not restricted to integer counts. K could be half. It could be 0.1. That would correspond to an even more tentative assumption of uniformity. When k is 0.1, you start assuming that everything is equally likely, but as soon as you get a few counts, some words will have a much, much higher probability than others. Right? Because some words would be 1.1 and the rest would be 1. The rest would be 0.1. We're also not restricted to adding the same pseudocount to all the buckets. We can choose to have a different number of pseudocounts to different words. That would correspond to the assumption that a priori we think that some words are more likely than others. And again, with enough data, it doesn't matter what we think. The data will override our initial pseudocounts. But with very little data, the choice of distribution of pseudocounts will make a big difference. Now these last two sentences that I said, that with lots of data it doesn't matter what you start with, and with very little data it matters a lot, should remind you of a prior. So you can think of those pseudocounts kind of like representing a prior. And in fact, they do represent a prior. So the nice thing about this method is that it has a very, very nice Bayesian interpretation. And the Bayesian interpretation has to do with a particular type of prior that these counts represent, and that's very easy to compute with. So to deal with that, we need to first think what it means to have a prior over a multinomial. So when I say that I have a prior over a coin, over the probability of head, this is a special degenerate kind of multinomial. It has only 1 degree of freedom, probability of head. And a prior over it prior over p head the probability of p head can be anything from 0 to 1, and a prior pi of p head would be something like this, that sums, the area here sums to 1, right? That would be the prior. For example, if I'm sure that a coin is fair, what would the prior be? It would be a delta function around 0.5. How about I'm fairly sure? I'm not 100% sure. I'm fairly sure, then it would look like this. What if I bought the coin at a magic shop?
You have less certainty, you probably would think it'd be a little biased towards one side.
Right. In fact, I would think that it's not likely to be a fair coin. Otherwise, why would I pay so much money for it? So if this is 1, it could look something like this. It's likely to be a coin that is biased, that is weighted somehow, so that it has more probability of being a head or being a tail. I don't know which one. And there is also the standard uniform. This seems simple, but it corresponds to something that's not natural for us. The thing is that any value of probability of head is as likely as any other value. That's not what usually happens in the real world. In the real world, we have some suspicion that it's either biased or that it's not biased, but that's a fair prior to. So that's for the simple multinomial of k equals 2. Yes?
What would the uniform distribution be? Like, what would the interpretation be again over a coin flip?
The uniform prior would be a prior that says that the probability density function for any value, for any continuous value between 0 and 1, is the same. Remember, this is not a probability distribution, this is a PDF, probability density function. The area of this is the same as the area of this, is the same as the area of this. They all sum to 1. It's a PDF. It's a mass. Yeah, I agree with you, right? It's hard to intuitive.
You just don't really know if it's fair or not fair. You just kind of don't have any idea.
Well, you don't know if it's fair or not fair, but actually this says that with probability 1, it's not fair. Because the only way for it to be fair was if the value was exactly 0.5. And the probability mass of 0.5 being a point solution is 0.
So you're actually more certain that it's not fair.
You are certain with probability 1 that it's not fair, but how much, I don't know. You can also combine the two. You can have a delta function here that accounts for, say, 70% of the mass, and the rest being uniform. This corresponds to saying there's a 70% chance that it's fair, and if it's not fair, it could be anything equally likely. I mean, any density function could be put here. So that's the simple case of k equals 1. In k equals 2, remember the probability simplex consists of, there's P1, P2, P3 in 3 dimensions, and the probability simplex consists of this triangle that connects, that covers this corner. Remember that? 2 degrees of freedom. Every point in this triangle corresponds to 3 coordinates that sum to 1. Now, a prior over this triangle is a probability density function, a PDF, that is defined over this triangular base and sticks out. It could be anything. If you are sure that it's a 3-sided coin, and you're sure that it's fair, then the center here is when they're all equal. This is not the origin. This is the point that is 1/3, 1/3, 1/3. And there would be a delta function sticking out of the board that all the mass is there. But if you're not sure they're equally likely, it might be a Gaussian or some other heel that's centered on this 1/3, 1/3, 1/3 and drops down. Or it could be uniform. The idea is that you're now building a PDF over an area, whereas here you built it over a line. So we want to be able to represent priors in this space. Remember that every point here corresponds to a whole multinomial. Okay, so priors live in a larger space than specific multinomials. These are priors over multinomials. In this case, the multinomial was a single point. It's a binomial. It's a single point. And the prior lives in a one-dimensional space, line. In this case, a multinomial is 2 degrees of freedom, 2 parameters, 3 parameters, but they sum to 1. So it lives in this 2-dimensional manifold, and the prior sticks out in the 3rd dimension. The PDF of the prior sticks out in the 3rd dimension. Since I reached the limit of my drawing ability, I will show you some nice pictures on Wikipedia. But what I'm really interested in is what happens in V dimensions, where V is 100,000. And in V dimensions, if the multinomial has V dimensions, that means it has V minus 1 degrees of freedom. And the prior is defined over a V minus 1 dimensional space. And itself lives in the extra dimension. So let me first give you the formula. There are many, many ways of defining priors over this high dimensional space, but there's one particular way that is very, very helpful, and that's called the Dirichlet. French mathematician Dirichlet. A Dirichlet, sometimes written as dir, with some parameters alpha 1 through alpha v, is a prior over the space of multinomials of, what do we call it there, P1 through PV. So if there are V words, V dimensions, the multinomial has V probabilities, only V minus 1 degrees of freedom. The Dirichlet, the corresponding Dirichlet, has V different parameters. They're all independent. You can choose them as you wish. They don't have to sum to 1. So you have V degrees of freedom here, V degrees of freedom, whereas here you have V minus 1 degrees of freedom. What do these alphas mean? They give you the prior, the probability that the Dirichlet, that the P1 through PV take on specific values. Let's say P1 takes value x1, P2 takes value x2, PV takes value xv, condition on the Dirichlet being alpha 1 through alpha v is, say, proportional, start with proportional, to the product of xi to the alpha I minus 1. So that's a succinct algebraic way of representing the probability of any particular multinomial. How do we understand what this does for us? Let's ask the question, what is the expected value of pi under a Dirichlet with alpha 1 through alpha v? And the answer, the expected value, is alpha I over the sum of the alphas. And what is the mode of pi? So expectation is the same as mean, right? Pi given the same Dirichlet. Now I have to remember which one is right, which one is alpha I, and which one is alpha I minus 1. You get the mode by taking the derivative. So alpha I minus 2. I better not take a chance and look it up unless my two TAs tell me which one is which. Yeah, I don't know. So let me show you some nice pictures of Dirichlet in 3 dimensions. And then Wikipedia will also answer that question. Let's try one more. No? Trying to get them both. Yeah, thank you. Okay, so first let me correct what I didn't remember. So the mean is alpha I, that's right, and the mode is alpha minus 1. Okay, so I was right, I just wasn't confident. The mode is alpha I minus 1 divided by the sum of alpha I minus 1. So the means are the normalized alpha i's, and the modes are the normalized alpha I minus 1. Let's look at these examples. So here we have, let's look at this beautiful picture. This triangle that you see Light. Never mind. Can you see it well enough? Should I turn off? I can turn off the light here. Okay, the thing to recognize is the triangle actually lives in three-dimensional space. It's the space of P1, P2, P3. It's the triangle that sits on the corner. Okay? So every point in the triangle corresponds to a particular multinomial over three outputs. P1, P2, P3 summing to 1. The point in the center, regardless of the hill, the point in the center corresponds to the fair three-way distribution. The points in the extremes correspond to a distribution where only x is possible. X is probability 1 and the other two are probability 0. And points along this line means that x and z have some probabilities that sum to 1 and y has probability 0. Okay? The height over the triangle corresponds to the density of the prior over that particular multinomial. Remember, there's infinitely many multinomials, there are infinitely many points in the triangle. Uncountably infinitely. So, what would be a good example? This guy, it looks to me like the peak and the center of gravity are not along the edges. They're not in the center either. They're kind of shied away from y. Right? But they're very symmetric with regard to x and z. So my guess is that the Dirichlet that corresponds to this density has a value of if this is x, y, and z, it would have the y. Y would not be completely 0 because it's not like everything is right on the edge. It's not. Y has some value, but it's smaller than what is indicated. It's further away from the center. So maybe y has a value of 1, and x and z have values of 5. So x and z are symmetric, and y is disfavored. Now, it doesn't have to be this. It could also be 50, 10, and 50. Notice that 50, 10, and 50, when normalized, are the same as 5, 1, and 5 normalized. So the mean and the mode would be the same. What would be different? The mean and the mode of this distribution would be the same whether it was derived from 5, 1, 5 or 50, 10, 50. Oh, you're right. The mode will be different. The mean of this distribution would be the same. Thank you. Because the mode would be 49, 9, 49 versus 4, 0, 4. So the mean would be the same. But more important for our needs is the variance would be different. When these numbers are larger, the distribution is more peaked. Remember that these numbers correspond to the pseudo counts, to the counts you put into the buckets. So if you put large counts into the bucket, what does it mean when you put these in? Suppose we put 5, 1, and 5 into the buckets before we throw in the real data. We're saying that we believe that x and z are equally likely to be anything. There's no difference between them. But y is likely to be smaller, right? So if we didn't get any data, the distribution that will come out of this would be 5, 1, 5. 5 out of 11, 1 out of 11, 5 out of 11. Now if we threw in 50, 10, 50, it's the same proportions, but it will take a lot more data to dissuade us from this. They're both 5 out of 11, 1 out of 11, 5 out of 11. So this is a particular distribution that is sort of the mean of both of these. All right, that's the alpha I over sum of alpha I. But having large numbers, or even larger numbers than that, let's say 5,000, 1,000, 5,000. Now if I start with this pseudo count, that means I'm pretty darn sure that this is the correct, or very close to the correct distribution, and I'm only going to allow the data to modify it a little bit, not by much. So this corresponds to, this corresponds to having the same, having the mean in the same location, but very, very peaked. A peaked prior means it pays less attention to the data, although at the end the data will rule if it has enough data. Okay, similarly, this guy looks like it is biased against X and also slightly in favor of Y, and is the treatment of X and Z the same? No, I think it's more.
So if you scroll down a bit, there are the numbers.
They do tell you the numbers? Okay.
In the description.
The
Description. Yeah, at the top.
at the top?
Yeah.
Oh, here. Excellent, thank you. Okay, so let's guess. Which is, okay, 626. That's the one we looked at, right?
Yes.
I assume it's XYZ. So I wasn't too far off. 515, 626. Okay. Good. So let's look at the others. I assume that it goes from top to bottom, from left to right?
It's clockwise from
I'm sorry?
clockwise from top left.
Okay, thank you. So we start with this one. We are very close to X and Y and very far from Z. And I think we're closer to X than to Y. And the answer is 622.
Yeah, because it's in the corner of X.
Yeah,
It's in the corner of X. So I can't see from here how far it is from Y, but apparently it's as far from Y as it is from Z. So it's symmetric with regard to Y and Z. Now let's look at this one because it's a milder distribution. It's not as peaked. And it's biased away from X and towards, and a little more towards D than towards Y. And it's the last one, 2, 3, 4. So it's only 2 for X, 3 for Y, and 4 for Z. So it's closer to Z and somewhat closer to Y and furthest from X. And because the numbers are relatively small, it's not very peaked. What would a 111 Dirichlet look like?
A mound in the middle.
It's not flat.
Centered around the center of gravity, like
Right. It's centered around the center of the triangle, and it's just very moderately curved, peaked. I'm sorry, 111, yes, 111 is flat. Thank you. What would a 222 be? It'll be a little mound. What would a 333 be? It'll be a little higher. What would a 1,000, 1,000, 1,000 be? It'll be very steep to right around the center of the triangle. Okay, the next question is what happens when these numbers are less than 1? And the answer is they become convex. So suppose you have a coin, a three-way coin, that you know is biased. So you want to exclude, or at least to discriminate against, you want to start with a less likely attribution of uniformity. Then you want it to be like a vase that's lower in the middle and larger on all sides. So you would make it maybe half, 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 or 0.1, 0.1, 0.1. And again, the closer it is to 0, the lower the curve is. A Dirichlet in 2 dimensions, when k equals 2, it corresponds to that coin example that we have, has a special name. It's called the beta distribution. So a beta distribution is a natural prior for a binomial, just like a Dirichlet is a natural prior for a multinomial. Why am I saying it's a natural prior? I just gave you one family of distributions called the Dirichlet and showed you examples of it. But there are many, many priors over the multinomial that don't fit into a Dirichlet. Why are we choosing the Dirichlet family? And the answer is because it's convenient. So let me tell you what I mean by convenient. we need to go back to the Bayes formula. In the Bayes formula, you have a prior. You get out a posterior in the presence of a likelihood function and the data. Prior is a distribution of the parameters. Posterior is also distribution of the parameters. And you convert this into this in the presence of a particular likelihood function and a particular data set. Okay? Now, the general rule for the posterior in the continuous case, it's the prior times the likelihood divide by the probability of the data, P of D, and P of D itself can be written as the integral over something that looks very much like this. Pi of theta, I'll call it theta prime because it's a dummy variable, it will be integrated out, times likelihood of data given theta prime, d theta prime. So this is integration over theta prime. In the case of the discrete distribution, this would be a summation. Usually, since theta comes from a continuous range, you need to do integration. The problem is, many times we come with a specific likelihood function, a specific prior, we don't know how to do the integration. We don't know how to solve it analytically. So it would be nice if, for a given likelihood function, we found a prior that we can solve analytically. There are, for many, many likelihood functions, there are priors that go with them that not only can be solved analytically, but that the answer belongs to the same family as the original prior. And that's called a conjugate prior. So a conjugate prior is a family of priors that has it's conjugate with regard to a particular likelihood function. It has the property that if you start with one member of that family and go through the Bayes machine using that likelihood function, what comes out is another member of the same family. So you can say that the family of a conjugate prior is closed under Bayesian updating with that likelihood function. And for most likelihood functions that people tend to work with, there is a known conjugate prior family. For some of them, we don't know what the conjugate family is, and for some of them we can prove that there is none. But for multinomials, the Dirichlet is the conjugate prior family. So, ooh, that's nice. Dirichlet is the conjugate prior family of the multinomial. And a special case is that the beta distribution is the conjugate prior family of the binomial. This is not a separate fact. This is when you apply it to multinomial with k equals 2, that's what you get. And if you go to Wikipedia or to any classic textbook on Bayes estimation, you will find a table of many, many known conjugate prior pairs. A likelihood function and a family of priors. Questions?
Closed under what? What's the?
Close under what I call Bayesian updating. Namely, if you start with a member of the family, if this came from a Dirichlet, if this was some member of Dirichlet, namely some values of alphas, and the likelihood function was a multinomial, then this is guaranteed to be another member of the Dirichlet. And in fact, I can tell you by heart what it would be, based on the parameters of alpha here and the data. We'll do it on Wednesday.
So basically, you could just take that process and just update it.
Exactly. It's very convenient. You can throw data in and update your prior to posterior, and the posterior is another Dirichlet. So you can move it to the beginning and throw more data in, and the output is another Dirichlet, and so forth. So you always stay with the Dirichlet, which is very nice.
When you're dealing with discrete distributions, is it still recommended to use priors from known families of conjugates, or is it okay to use?
It is okay. It is okay to use whatever you want, because the calculation, assuming the number of categories is manageable, you can explicitly calculate this, right? So yeah, then
In terms of language, you mostly dealing with like finite sets.
yeah.
But you still see a lot of people using Dirichlet priors.
Well, I don't want to